Hello, y'all. Darrell Berry Jr. back as promised, doing some called oscillators. I have the Taylor book shown as I'll be looking through Taylor. I just realized my image is showing crazily. I'll fix that while I'm giving you the preamble. But I have my Taylor book showing because I'll be reading through Taylor, but I'll be looking through other resources as well, not just that. But also that's the main one I'll look at since my professor suggested that book to read through. And let me adjust my image for the show, seeing that it's showing be better. So we'll just a couple of oscillators. Everything looks good, I think. Yeah. So we'll go ahead and jump right in. I have my other resources up, including the exam I took for foundations and the feedback professor gave me on those. So we'll be going straight to the notepad today. Well, this video. So the idea that we're looking at is, let's see, a card or something. Another card. Wheels. We have that they're on. Then we have three springs that are connecting them. So we have two. K is the spring constant. K1, K2, and K3. That's what we're looking at. And a couple oscillators in normal modes. This is chapter 11 in Taylor. In chapter 5, we discussed the oscillations of a single body, such as a mass on the end of a fixed spring. I now want to take up oscillations of several bodies, such as the atoms that make up a molecule like CO2. So where this is applicable. Molecules, which we can imagine as a system of masses connected to one another by springs. If each mass were attached to a separate fixed spring with no connections between masses, then each would oscillate independently as described in chapter 5. And there would be nothing more to say. Thus, our interest here is a system of masses that can oscillate and are connected to one another in some way, a system of coupled oscillators. A single oscillator has a single natural frequency at which, in the absence of damping or driving forces, it will oscillate forever. We shall find that two or more coupled oscillators have several natural or normal frequencies, and that the general motion is a combination of vibrations at all the different natural frequencies. Like the theory of rotating bodies in chapter 10, the theory of coupled oscillators makes essential use of matrices, and many of the ideas you learn in chapter 10 play an important role here. The most obvious application of the ideas of this chapter are through the study of molecules, but there are many others, including acoustics. That's how sounds blend, bridges, uh, and buildings coupled electrical circuits. Throughout this chapter, I shall assume that all the forces with which we are concerned will be Hooke's law. So Hooke's law is going to be F, the force equals negative AX. And hence that the equations of motion are all linear. While this is a special case, it is a very important special case with many applications in mechanics and throughout physics. Nevertheless, you should bear in mind that the systems discussed here are a special case. We shall see in chapter 12 how startlingly more complicated the motion of nonlinear oscillations can be. So we're focusing on linear oscillations. So now we have two masses. This is, by the way, chapter 11 of Taylor. Masses and three springs, which is what I have written here, drawn here. As a first simple example of coupled oscillators, consider two carts thrown in, I'll call this figure 1. The carts move without friction on a horizontal track between two fixed walls. Let me copy this out, and I'll add in some details that Taylor has. Two. So we have this point here and this point here. This is equilibrium. Equilibrium. This is when they're at rest. And actually let me offset it a bit. So at that point is where they would have been in equilibrium. Here is where x1 is, and here is where x2 is. So x1 and x2 are measured from equilibrium. The k's are connected to each part as shown. The parts have their respective masses. Let's say there's spring 2 that couples the two oscillators. So this is the coupling spring that blends their normal frequencies. In fact, spring 2 makes it impossible that either cart move without the other moving as well. For example, if cart 1 is stationary and cart 2 moves, the length of spring 2 will change, which will produce a changing force on cart 1, causing it to move as well. And you say, in the following discussion, it is simplest to assume that when the two carts are at their equilibrium positions, the three springs are neither stretched nor compressed. Their lengths are equal to their natural unstretched length. However, depending on the distance between the two walls, it could be that all three springs are compressed or all three are stretched. Fortunately, as you can easily check, none of the results of the next three sections is affected by these possibilities. All right, so it doesn't matter if, as long as they're in equilibrium, it doesn't matter if the springs are compressed or they're stretched out, it should move in exactly the same ways. All right, so that's good to know. It is easy to find the equations of motion for the two carts using either Newton's second law or Lagrange's equations. In general, Lagrange's equations are easier to write down, but in the present simple case, Newton's law may be a little more instructive. All right, so why don't I go through each of these and see if we come to the same equation. Um, um, hinted to. So what I'll do is start with newtons. So we know that F equals negative kx, and what we can do is look at our system and say that F, the force on mass 1, equals m1 a1, which equals m1 x1 double dot. So if we look at this, if we were to move part 1 by position x1, it'll feel the force from the first k1. So that's going to be negative k1 x1. And if we move it still again by x1, it'll also feel the force by k2. So we'll consider, like if we had a single box case, F will be negative kx. So we'll consider the force of the spring if we move towards the right from equilibrium. It's going to pull it back, the restoring force, going to pull it to the left. So if I move the mass to the right, the force will put it to the left. As we have the negative there, it's opposite the opposite whatever direction we move that. So by the same token, if we move the mass to the left, the spring force will push it to the right. So those will be negative x, and these two negatives will make it positive. So the force will be to the right. So we can see how it's a restoring force. It always moves opposite. So we can say if it pulls to the left, it's negative kx. If I push x1 to the right, k2 pushes it to the left as well. So we have negative k2 x1. But in this case, k2 will move x2 to the right. So if I move this x1, k2 is going to push on mass 2. So it's giving the opposite effect. So I'll do plus k2 x2. So I'm moving x1, but k2 is moving x2 to the right. So that's the force that k2 is going to feel, opposite what everything else is feeling. And if I have F2 equals M2 A2 equals M2 X2 double dot equals. So if I move M1, K2 will move M2 to the right. So we have plus K2 X1. And if I move M2 by X2, K2 is going to pull it to the left. So minus K2 X2. And if I move X2 to the right, K3 is going to push M2 to the left. So it's going to be minus K3 X2. So we see K2 is doing double work because K2 is connected to both masses. But on one hand, K2 is pushing to the right. For the second force, if I move X1, and K2 is pushing to the right as well. If I move X2 to the right, it's moving X1. So there's that all one where K2 is moving to the right if we move the opposite mass. So I'll move x1 is forcing x2, m2 to the right. We'll move m2 is forcing the force on x1 to the right. I think I said that right. So to simplify this, F1 equals M1 A1. Actually, let me X1 double dot, which equals, so the best thing to do is to extract out the x's. So we have negative K1 plus K2, X1 plus K2, X2, and we have F2 equals M2 X2 double dot, which equals K2 X1 minus K2 plus K3 X2. So this seems to be the equations of motion. I noticed that the textbook and the way they do it here, they divide by M. But I like dividing by M because that's how I learned it in my undergraduate. I'm tempted to try to do it the other way, but I also want to try to build on what I know. So I think I'll try the way I learned it in undergraduate and see if I get the same answers what they're doing. But I just may have forgotten too many details or something and just have to learn it a different way. So, but we haven't gotten there yet. So also I'll do the Lagrangian method of getting the equations of motion. So Lagrangian, and I think I'll copy the graph down again, so I'd have to keep scrolling up this far. Lagrangian, it is done in undergraduate, but it's definitely more relevant to graduate stuff, like when we do orbital mechanics and stuff that we're starting to get into, and the rotation of three-dimensional bodies. Um, Lagrangian is a big part. I'm still not clear on some details that I'll have to ask my professor about. Like force is, let me move this down a bit here. So the way it works is force is the negative change in potential. So that means that potential is negative the integral of force. But yet it does not seem to work out when I try to do the potential for Lagrangian in this way. Maybe I'm doing an integral wrong or something. But if I'm looking at this, the Lagrangian is going to be the kinetic energy minus the potential energy. So P is going to be 1/2 mx dot squared 1/2 m2 x2 dot squared. Easy enough. It's just the kinetic energy of the thing. So let me actually adjust my position a bit here. I'll make myself a little taller in my seat, but I gotta raise my boom a bit. Happen? All right, that's better. So now I'll do the Lagrangian formulation. So we have that, and we have potential equals now. Um, like for instance, let me show you what I mean. I'll take, maybe I just did my derivative incorrectly. But of course, that's the equation of motion. Maybe that's why. Oh, right, it's the force. Probably because it's just a different formulation. Maybe that's why it doesn't work. You can't take the potential from the equation of motion. I'm not sure. It's some detail I have to ask professor about. But all right, if we look at this, all right. So let's back up. Go here. Actually, I could just leave this there. So that means that v equals negative integral negative kx, as we're dealing with the spring constant. So we have k x2 divided by 2, which is 1/2 kx squared. That's the potential. So if I look at mass 1, and I just focus on mass 1, it's the potential that mass 1 gets from that spring. So if I move mass 1, that spring will give it some potential energy, just like raising something above a above the ground. So I'll have negative k1 x1 squared, and if I move a x2, the mass 2 to the right, is going to experience a potential energy, and it should be negative. Oh, I just not write my 1/2. All right, there we go. So this will be, the force is also pushing it to the left, like this force. Just that spring will give it the same potential. Well, actually, that potential is not direction-wise. And plus, I'm manually pushing it to the left, but potential is not direction dependent, so I shouldn't have to worry about the negative. So if I move this mass to the right, let's say I move it to the right, it will have that potential to push back, just like moving something up. So this will also be 1/2, but it'll be k3 x2 squared. And the thing about the middle spring is if I move mass 2 and then I move mass 1, if I move mass 2 this way, K2 will give it a potential like plus 1/2 K2 x2 squared. But if I also move mass 1, this distance will change. So it won't be only the distance x2, it'll be x2 minus x1. So the potential energy that M2 gets from that spring will be the difference between the two. And the same thing with the potential that, well, I guess we could only focus on one mass, because there will be the potential between the two. So this potential here is the potential of the distance between these two. This potential here is the distance from there to there. This is the potential from there to there. This is the potential between the two masses. So if I move just M2, the potential between the two masses will be like just as if there's a wall here. And it'll just be the normal potential like I wrote there. But if I move x1 as well, let's say by the same amount, then there's no potential. So it'll be x2 minus x1. So we can consider that potential the potential between the two masses. So this will be k2 x2 minus x1 squared, because that distance is x2 minus x1. The distance between them, the single distance. What if I could just call that x3? No, that'll just complicate things. So now we have 1/2 k1 x1 squared plus 1/2 k3 x2 squared plus 1/2 k2 x squared minus 2 x1 x2 plus x1 squared. And now we have our potential for the system. So unplug this. That'll give me some more room as well. So now I have my Lagrangian for this system of two masses connected by 3 springs. So now I can connect these together, and maybe I'll simplify this some. Yeah, let me simplify this some. So I have 1/2 k1 squared x1 squared plus 1/2 k3. Oh, added an extra squared on my k3 x2 squared plus 1/2 k2 x2 squared minus, so the 1/2 and a 2 will cancel, k2 x1 x2 plus 1/2 k2 x1. And that's all the terms. So what I end up with is v equals I simplified too much because they're each dealing with different springs. So there's something I could simplify here. 1/2 k1 x1 squared plus, I'll just put k2 in the middle, and I'll have 1/2 k2 x1 squared plus x2 squared minus x1 x2. And then we have lastly plus 1/2 k3 x2 squared. I have them in order by my k's. 1/2 k on x1 squared. At the end, 1/2 k3 x2 squared. In the middle, we have the 1/2 k2. Oh, but I took out an extra 1/2 factor, so I got to add the 2 back. We have 2. 1/2 k2 x2 squared plus x1 squared minus 2 x1 x2. I think that is correct. So that means my Lagrangian is now 1/2 m1 x1 dot squared plus 1/2 m2 x2 dot squared minus 1/2 a1 x1 squared plus a2 x1 squared plus x2 squared minus 2x1 x2 minus 1/2 a3 x2 squared. And maybe I could still put them all on one line. We have our Lagrangian. Check my notes. I got this part right before. I'll make sure I didn't make a typo somewhere. Oh well. I'm actually and the other problem, the k's, we had specific values for k's, but this is, I would say, is the most general case. So if you're doing this problem most generally, this is the most general case. Oh my gosh, added an extra 1/2 here. This is the most general case. So whatever type of problem you're doing, this will work even if they give you different k's or the same k or different masses or the same mass. This is the equation you would get for the Lagrangian. It's like this is the equation you would get for the equation of motion. But we'll see if we get the same thing for the most general case. And I can't necessarily check what I did on the exam because I used the specific values. But I mean, it seems pretty similar. But divvy out the 1/2. The cross terms are a bit different because the k values that we had, but I'm pretty sure it's fine. So we'll keep going. We'll see if I get the general case. So the, what do you call it? Lagrange equation is the full time derivative of well, first let me say that our generalized coordinate is, we have two of them, x1, well, let's put it this way. Lagrangian is a function of x dot t, and let's say x1 dot and t, and x2 dot and t. So that might not be the official way to write that, but so I'll do each of those. So we'll do x1 first. So we have d dt, the full time derivative of the Lagrangian to the x1 dot minus partial Lagrangian x1 equals 0. So we have d dt, and let's take the Lagrangian with respect to x1 dot. So we have this term here has x1 dot, so that's m1 x1 dot minus, so we have to look for all the x1s. So we have an x1 here. Oh, and hold up. I love the parentheses off right here. Right? So we have minus, because the Lagrangian is minus the potential. I could extract the 1/2, but I have to minus that whole potential, K1, 1/2. So that's extracting 1/2. Okay, everything looks good. And again, when I factored out the 1/2, I get to divide by 2. Make sure I have my 2 properly. Divide by 1/2 times 1/2. Divided by 1/2, multiply by out, divide by 1/2 times 2. Yep, so we're good. So these are my x's. I have an x here. Fraction is there properly. So we have negative a1 x1, and then I have a x1 here. So it's going to be negative. The 1/2 is going to distribute k2 x1, and then I have a x1 there. So the negative will distribute, the negative 1/2 will distribute there. The negative 1/2 and the k2 will distribute there. So it'll be plus k2. The negatives cancel. Then we take the derivative with respect to x1. So it'll be x2. And we should have that. And it's minus all of that. So I have to put a minus there. And it should be it. I'll just keep going and I'll check it later. And this equals 0. We have m1 x1 double dot equals negative k1 plus k2 x1 plus k2 x2. I'm going to bring that to the other side. And I believe that is what I had before. This is negative 1 plus k2 x2. All right. So now all we have to do is get the other version, the x2 equation. Let's see if that matches the Newtonian formulation. So we have x2, so that's d dt for the Lagrange's equation, partial Lagrangian, partial x2 time derivative minus partial Lagrangian over partial x2 equals 0. So we have d dt. So I'll look for the x2's in my Lagrangian so it doesn't get lost. That's the Lagrangian right there. So I see that I have an x2 dot here. That's my only x2. We have m2 x2 dot minus. So now I'm looking for x2. So I have an x2 here. So the negative will distribute to the a2. So that'll be double negative. So that makes it positive. And when I take the derivative, it'll just be k2 2. then it's still minus because it's minus the whole thing. I have an x2 here. So we have the negative distribute to the k2. I'm subtracting it, so it's positive 1/2 k2. But the 1/2 will go in. So that's just positive k2. But then a negative is a negative on that. So to add another negative, I'm taking the x2 derivative. So this will give me x1. And then we have another minus, but there's a 1/2 there. So it's plus k3 x2 for this last one right here. So now I'll simplify this. So I have m2 x2 double dot. And then I'm going to bring everything to the other side. So I have minus k2 plus k3 x2 plus k2 x1. And this equals f2. That does seem to be what I had for the Newtonian case. K2 plus x2 plus k2 x1. All right. So we can see that both the Newtonian and Lagrangian formulations give us the same equation. And we're doing this in the most general case. So whether they give you this k equals 0 or that k equals 0 on the end, you could just make the k respective k equals 0. They give you the same equation. If the masses are the same masses or different masses, you could just plug in what the masses are, and it'll give you the same equation. So okay, so that's the equations of motion. Now it says in the title linear algebra. So we're going to go to the linear algebra part of this, and this is the part that I keep messing up on. The normal modes. I hated this when I was in undergraduate, when I was actually taking this class. First, I had another stand here. Put this. I have to get another stand. I do actually have another stand in storage. I'm gonna have to get my other stand to make working with my CAD easier. So I'll give myself some space like so. So all right. So looking at the normal modes of this thing, which is basically if I move this mass to the right, spring K2 is going to operate only on that, but K2 is going to make mass 2 move. And you know, if I move mass 1, it's going to stretch this spring. And let's say if I hold it there, K2 is going to initially contract a bit, but then it's going to push out on mass 2, and it's going to be again at equilibrium. So we're going to have K1 stretched, and we're going to have K2. Am I erasing too much? So we're going to have K1 stretched. We're going to have K2 in equilibrium. And when I let K1, M1 go, it's going to start oscillating. But now we're going to remove the pressure on K2. So K2 is going to start oscillating M1. And of course, the same thing is going to happen with a domino effect with M3. So the whole thing is going to be moving in a certain mode where they're all set. And it's a mirror image if I did that to 2. But at the same time, if I move both M1 and M2, they're going to operate together in a certain way. So these are different ways of looking at the different modes of the way this thing oscillates, depending on whether one is moved farther than the other one, or whether they're moved in the same direction, or they're moved in the same way in opposite directions. If we move M1 to the left and M2 to the right, you know, K1 will be be compressed to the left, K3 will be compressed to the right, K2 will be stretched in either direction, and but however we move it, it'll simplify and blend into certain normal mode frequencies. You got to try to find those normal modes. So the way we can look at this is I can take the equations of motion. So we'll put normal modes. We have here just of motion. So I have M1, X1, double dot equals negative K1 plus K2, X1 plus K2, X2. And again, I'll try to do this in a way I'm familiar with. See if I get the same answer. I'll just do it a lot more carefully. So if X1 double dot equals negative K1 over M1 plus B2 over M1, X1 plus K2 over M1, X2. And M2, X2 double dot equals K2, X1 minus K2 plus K3, X2. So X2 double dot equals K2 over M2 X1 minus K2 over M2 plus K3 over M2 X2. So I'll call K1 over M1 omega 1 1. I'll call K2 over M1 omega 2 1. I'll call K2 over M2 omega 2 2. And I'll call K3 over M2 omega 3 2. And omega squared equals K over M. So I'll say omega squared ij equals Ki over mj. So this is actually squared. Right? So it's a sort of an aside for notating. So I can say one dot dot x2 dot dot equals, we have omega negative Make sure, let me highlight this. This is what I'm looking at putting into matrix form. So I have, for the first one, negative omega 1 squared plus omega 2 squared. And then we have omega 2 squared. X1. And we have plus omega 2 over negative omega 2 plus omega 3 squared x2. And anybody who pops in, if you have any questions, let me know. So we have x dot dot, that's a vector now, equals negative, I'll just remove the parentheses, negative omega 1 squared minus omega 2 squared and omega 2 squared, omega 2 squared minus omega 2 squared minus omega 3 squared. And then we have that, which is a vector. Make sure my notation doesn't mix me up. I'm going to name this something else, A, B, C, D. I could name this something else to make this smoother. So I'll call omega 1, omega A, omega 2, omega B, omega 2, omega C, omega 3, omega D. So what this means is I have the vector of the acceleration equals minus omega A squared minus omega B squared and omega C squared, omega B squared, omega C squared minus omega B squared. And this is times the vector here. So we have this. Maybe I could skip this step here and just call them omega A, omega B, omega C, and omega D. So that should save some time. So I might do that next time. Right? So I think this is correct. And what we can do here is we can say, what I'll do is just call this matrix uh, omega. So I'll just make sure I just call it matrix capital W. So if it's lowercase as a vector, if it's capital, it's a matrix. So we can say that W x can equal lambda x. And actually, this right now is just a constant. So it is a vector. And we can say that the lambda vector is non-trivial to use the textbook from Bowles, even though I hate when they use trivial because usually it means that they're making something sound simpler than it is. But like saying equals not zero. If and only if, that's a math term. So let me show the if and only if. So if I take omega x minus lambda x equals zero, and I can factor this out and say omega minus lambda x equals zero. And again, this is a matrix, and these are vectors. And I can say that this matrix minus lambda identity matrix x equals zero. So this is if and only if the determinant of matrix minus lambda I equals zero. So only when that determinant equals zero can I find a lambda that makes this work. And the lambdas will be calling our eigen value or our normal frequency. That's what we're trying to find. So I'll call this determinant omega minus omega I equals zero. So that's going to be the determinant of negative omega a squared minus omega b squared minus omega b squared. And hold up, I'll call this omega squared. Omega squared. Let me give myself a little bit more room. I think that's one of the things that confused me on my exam. I kept it lambda. I'm actually going to call it omega now and squared. So it matches omega squared. Now we have omega c squared. And now we have minus omega c squared minus omega b squared minus omega squared. equals 0. So it's going to be some math. We're going to have negative omega a squared plus omega b squared plus omega squared times negative omega c squared plus omega b squared plus omega squared minus omega c squared omega b squared equals 0. So if I was to multiply this out, we would have omega a squared omega c squared. I'll do the a's first, plus omega a squared omega b squared plus omega a squared omega squared plus, now I'll do the b's, plus omega b squared omega b squared c squared plus omega b squared omega b squared plus omega b squared omega squared plus, then I'll do the last one, omega squared omega c squared plus omega squared omega b squared. Oh, chat. Let me see what we have here. When you do multivariable integrals, where you have to go from rectangular to spherical, rectangular to cylindrical, and spherical to cylindrical. Yeah, I could do that. It's been a while. But yeah, I was actually pretty good with that. You mean like, I forget the exact word for it, but like let's say you have a function and you have to rotate the function about the axis and then get the volume or area of the rotation. Yeah, I'm familiar with those. So I can make a video about that in the future. Maybe I can make a video about that tonight for my regular show. It'd be a good break from the actual stuff I'm doing. Yeah, those are pretty cool. I actually think they're pretty fun. I like integrals. I'll tell you what, just my regular show is at 8 p.m. Central Time. So I'll plan to do a video like that then. So that's 4.5 hours from now. So I'll finish this problem as far as I can and take a break and get something to eat. And then I'll do a show on multivariable integrals at 8 p.m. Central Time, which is 4.5 hours from now. So you can look forward to that. So I'll look for you then. So we have this. You're welcome. Sounds good. Sure, it'll be a good time. So actually, pretty fun when you get the hang of them. So we have the last one, omega squared, omega squared. All right. We have WA. Let me just make sure I got everything right. We have WA, WC, WA, WB, WAW. We have WB, WC, WB, WB, and WBW. We have WWC, WWB, WW. I'm so tempted to give these things some values and discontinue doing a general case. So many terms, but I shall continue doing the general case. I'll keep doing it unless I like can't do it anymore. But I mean, it's tedious, but it's not. It's all right. I'm looking around. Oh, you know what? I'll just lean my pad on this book here. That'll give me a bit of an angle there. Uh, all right, here we go. So what am I doing again? I'm taking the determinant, setting it equal to 0, and I'm trying to solve for omega squared. So let's go ahead and simplify this. So I have omega to the fourth. I have plus, so I have an omega squared there, omega squared, omega a squared, plus omega b squared, plus omega c squared. Oh crap, I have two omega b's. Oh no, it's omega, sorry. So I got ABC. That seems good. Oh, am I missing one? Oh, there's two omega b's. All right. Why is that? Let me make sure. Yeah, I do have an omega b here. I do have one there. So I do actually have two omega b's showing up uh, on that multiplication outward. Oh, and then I have another one here, but that's with C. But I do have two omega b's that are being multiplied into the omega, the, with no subterm on it. So, okay, so that seems all right. Was that so now I'm going to just add a 2 into to the front of that one. Where did I put the second omega b at? Yeah, here. So I have 1, 1, 2, 3, 4 omega terms with the letters. So I'll just plop a 2 right here. I think that takes care of that. I'm going to go very carefully to make sure I don't miss anything. I should do these in different colors or something. I'm starting to mix up which one I'm looking at. So that was that one. This is this one. Extracted out the omega squared. Okay, that looks good. And then we have plus. So what is a good way to factor these? Maybe I should do a different color. We have this one, we have this one. This one, we have this one. So all of them, nope, I can't see anything that they all have. Oh, hold up. Just realized I have a second. No, never mind. I got that. Yep. It is a constant. I can't see any way to simplify that. So, I can go omega a squared, omega c squared plus omega b squared plus omega b squared, and that's omega b squared plus omega c squared. So I just put these two the omega A's with omega B and C. And then I put these two, the omega B's with omega B and C. Omega A with omega B and C, omega B with omega B and C. I miss a term. Oh, I did miss a term. I think I missed this term right here. 3, 4, 5, 6, 7, 8, 9. Yes, I did. This is a minus. I'll actually change the style of this and put that 1, 2, 3, 4, 5, 6, 7, 8, 9 minus that term. But let's see if that cancels out something. WC squared, WB squared. It does. Minus WC squared, WB squared. So it looks like it actually cancels out this. So there's a minus WC squared, WB squared, and there's a plus WC squared, WB squared right there. So this equals W4 plus omega squared. Oh, no, it's about to say I could factor that or something, but WA squared plus 2 WB squared. And that's omega actually, but I'm just used to calling it W plus WC squared plus C. Um, let's write it out really fast. See if something shakes itself out. WA squared, WC squared plus WA squared, WB squared plus WB squared, WB squared. I think that is correct. It's a double up on the B. What was B again? 2, 1. 2 in mass 1. And there is a double up on the 2K mass 1. There's double up on the 2, 2. I think this is correct. I think that's it. This is so complicated to solve though. Maybe I do need to give these things some values. Um, say that, let's check one more time. Yeah, I'm about to give these things some values. This is like, it's ridiculous here. So Taylor gives one where all the values are the same. But let us go ahead and do M1 equals M2 equals M. K1 equals K3 equals K, and K2 equals 2K. So WA equals W11 if I recall. So that equals K1 over M1. So that equals K over M. So WB squared equals, I believe that's 1, 2. Nope, V is 2, 1 equals W21 squared. So they're going to be K2 over M1, which is going to be 2 K over M. WC squared equals, C was the 2, 2. W22 squared. Again, that's omega, but I call it W. So that's K2 over M2, which equals 2 K over M. And omega D squared, that should be 3, 1. No, 3, 2. Yeah. Omega 3, 2 squared equals K3 over M2, which equals K over M. And this is on the side. We give them some values. So this means this equals omega to the fourth plus omega squared. And we have WA squared is K over M plus 2. WB squared is 2 K over M plus WC squared is 2 K over M plus WA squared is K over M. WC squared is 2 K over M plus WA squared is K over M. And WB squared is 2 K over M plus WB squared squared. So that's 2 K over M, 2 K over M. W squared, W2. We need to close that. Yeah. The A squared, K over M. WC squared 2 times 2 K over M. WC squared 2 times K over M. The A squared, K over M. WC squared 2 K over M. WA squared, K over M. WB squared 2K over M. And then WA squared So WB squared K over M and WB squared. Should I miss anything? All right. So we have omega 4 plus omega squared be 1 K over M plus 4 K over M plus 2 K over M. So 1 plus 4 is 5 plus 2, that's 7 K over M. 4, 2, I think that's right. Plus so this is going to be 2 K over M squared plus 2 K over M squared plus 4 K over M squared. So this is going to be omega to the fourth plus omega squared 7, and I'll call this omega naught plus 2 omega naught squared 4 omega naught squared, which is 8 omega naught squared. I believe that works. Algebraically, it seems to work. All right. So now we have when this equals 0. So now we have omega squared, omega squared. We have plus, oh, oh, omega naught squared, plus 7 omega naught plus omega naught. And to multiply this out, we have omega to the fourth plus omega naught plus this has to both be squared. Be omega squared equals 0 plus 7 omega naught squared plus omega naught squared equals 0. So I multiply this out. This is omega to the fourth plus omega squared, omega naught squared plus 7. Oh, hold up. Still not working. I do have to use the what's my call? Hoping I can factor this thing. Yeah, so be it. I need to remind myself how to complete the square. I actually like that method, but I don't actually remember how to do it. So we have negative b omega squared equals negative b plus minus square root b squared minus 4ac all over 2a. So we have omega squared equals negative 7 omega naught squared plus minus square root of b squared 49 omega naught 4 minus 4 1 8 omega naught squared all over 2. We have that it equals 7 negative 7 omega naught squared because we're solving for omega naught squared. That get there. I'll put x equals omega squared. Omega squared equals x. So that equals negative. Oh, I have to erase the whole thing. Hold on. Simplify all these squares. So this is x squared, this is x, and that doesn't have an x. So I guess you could say it's x to the 0. So negative 7 omega naught squared plus minus square root of b squared, so 49 omega naught to the 4th, minus 4 is 1, c is 8 omega naught squared over 2a over 2, that seems right, plus minus square root of 49 omega naught to the 4th, minus 4 times 8, that's 32. Omega naught, hold up, so the omega naught squares, you know, put this expression here. I believe it should be squared as well. Let's keep going and see where it goes. Over 2. Let me check what I did before. I see what I did. This is omega naught squared equals omega naught to the fourth. That's the same mistake I made before. So I got to get used to that. Let me add an extra line here. See if I can get this in one swipe. There we go. So we have this equals omega to the fourth plus omega squared 7 omega naught squared plus 2 omega naught squared plus 2 omega naught squared plus 4 omega naught squared. This is 2 plus 2 plus 4. That's 8 omega naught squared. So that's omega naught to the fourth. So this is omega naught to the fourth. So this is 32 omega naught to the fourth. All right, so now we're looking good. So we have negative 7 omega naught squared plus or minus square root 17 omega naught 4 over 2 which equals negative 7 omega naught squared plus or minus, I'll say x1 equals is square root of 17. Is that something? Has to be an irrational number, right? You see how bad it is. 4.12. Should I round it up to 4? I think that won't be too much of a rounding. It's almost 7 omega naught squared plus or minus 4 omega naught squared over 2, which equals So x1, which is omega 1 squared, equals -7 plus 4 omega naught squared divided by 2, which equals -3/2 omega naught squared, and x2, which is omega 2 squared, equals -7 minus 4 omega naught squared over 2, which equals negative 11 over 2 omega naught squared. Dare I round this some more? I think that's all right. These are my C's, eigenvalues, to use linear algebra term. All right. So see what I did incorrectly on this again on the original one I did. Hmm. Said I should get Q over M when I simplify this. So that means I did something incorrectly up here. What I'll do is I'm gonna go back to this step. I'm gonna go back to the first step and see what happens if I start from the beginning with the uh putting the values in. Again, so we have dot equals negative 8 over M plus 2 A over M x1 plus 2 A over M x2 x2 double dot equals 2 K over M x1 minus 2 K over M plus K over M 2. So we have x1 double dot equals negative 3 K over M x1 plus 2 K over M x2 x2 double dot equals 2 K over M x1 minus 3 K over M x2 which equals negative 3 omega naught squared x1 plus 2 omega naught squared x2, and this equals 2 omega naught squared x1 minus 3 omega naught squared x2. So we have the vector double dot equals the matrix negative 2 omega naught squared 2 omega naught squared negative negative 3 omega naught squared 2 omega naught squared 2 omega naught squared negative 3 omega naught squared, and then we have the vector x. And as we said before, we call this w. You can say w x equals omega x, where omega I is the eigenvalues or the eigenvalue for, what is it again? Normal frequency. And we can do like we did before. W minus this equals 0. Which is W minus omega I equals 0. And now we're back where we were with the explanation here, even though my whose columns are different. I'll just copy this down. To make this omega squared. So now we have determinant is omega, or W, the big W, minus or omega squared is going to diagonalize the answer equals 0. So we have the determinant of -3 omega naught squared minus omega squared 2 omega naught squared 2 omega naught squared -3 omega naught squared minus omega squared equals 0. So we have 3 omega naught squared plus omega squared 3 omega naught squared plus omega squared. Factor out the negatives. Minus 4 omega naught to the fourth. What is the fourth I missed before? So we have 9 omega naught to the fourth plus 3 omega naught squared plus 3 omega naught squared plus omega to the fourth equals 0. So we have omega to the fourth plus 6 omega naught squared plus 9 omega naught to the fourth equals 0, which is x squared plus 6 omega naught squared x plus 9 omega naught to the fourth equals 0, and x equals omega squared to a message real fast. All right. I think this looks good. What's this different from the last one? I don't know what I did before. I guess it was just all those variables. I must have just mixed up one of my variables or something. This look more like what I had before. I don't know. All right, let's keep going. Pretty sure this is the rightest right one. I still don't think I can factor. Maybe I can. X 0 3 omega naught squared plus 3 omega naught squared. I think that works. So to test this out, I have x squared plus 3 omega naught squared x plus 3 omega naught squared x plus 9 omega naught to the fourth. Check out equals x squared plus 6 omega naught squared x plus 9 omega naught to the fourth. All right, I think that's it. Our Reba says these problems are a little frustrating since a typo anywhere will go unnoticed and you can end up with an impossible looking integral. Well, these problems here, this should not give me an integral, but you are correct about the determinant and the resulting value for x. So I messed up on one variable here, I don't know where I messed up at, but I messed up somewhere. And my what do you call it? Forgot the exact formal word they called it. The resulting function, I don't know, whatever it's called. But my what do you call it? This formula here that I remember how to write, but I don't remember the name of it at a particular moment. This came out absolutely ugly. It was just ugly. And I know from professor that I should get a pretty even normal frequencies. So like I said, it's one little detail I mixed up. Yes, I meant the determinant would result in a polynomial with weird roots. Yes, it is crazy. One little mistake. So this whole, I mean, it's still good practice going through it, I guess, but I did mess up all this work. So I mean, of course, there's a way to do it. I just have to be more careful with whatever my variables I use. But I'll just continue with this. All right, let's see if we can get a natural answer this time. So that means that x1 equals negative 3 omega naught squared. Hold on. It's the same damn thing? Yes, it is. That is not, I swear that's not what Professor had before. Mess something else up? Maybe I did. It should be different though. Huh, what did I do wrong again? No, that's what I did. I forgot the term. I keep leaving off this damn term. I left it off the last time as well. The last term right here. So this term I left off. I said term. All right. So when I include that term, then so that means I got to erase all of this. That was just too easy. Oh, you dropped the term. Yep. Thanks. Thanks, Ari. Ari. Thanks, Arib Ahmad. Awesome. Thanks for pointing that out. I'll try to look at the chat a bit more quickly. We'll caught that sooner. Right. Now we have this. So I'll just bring it down one more time. What the hell? So we have that written. So now I'm going to have omega to the fourth plus 6 omega naught squared omega squared plus 5 omega naught to the fourth. Okay. Now this is seeming more like it should be. Yes. Because in the original one, I did have a square root of 5. So it looks like I did get that. I did it totally, I guess not totally differently, but I did it differently. And I did end up with a square root of 5 on this thing. So this is looking up. All right. All right. So let's keep on going. So I will say uh, x squared plus 6 omega naught squared x plus 5 omega naught fourth equals 0. And x is omega squared. And can I factor this? I think I can. So we have x uh, x equals 0. So it seems to be a quick 3 and 2. Looking at that right. 3 omega naught squared 2 omega. Nope. Crap. I'm thinking about this part and not that part. Yeah. Crap. I wish I remember how to do the completing the square. I like that way. I got to look that up again or something. Damn it. Because I just hate this more. X equals negative b plus minus square root b squared minus 4ac over 2a. I had a class in undergraduate. Oh, and Ahmad says if you have a fifth power, then you know you messed up because these problems are meant to be solved with substitution. Let w fourth equals a squared and use the formula. That's a good way to know you ended up with something reasonable. Yeah, I agree. Some good advice from Ahmad there. So we have this. So we have x equals negative 6 omega naught squared plus minus square root of, so we have 36 omega naught to the fourth uh, minus 4a 5 omega naught to the fourth over 2. This gives me negative 6 omega naught squared plus minus uh, you know, it does end up being 16 after I did the simplification earlier. 36. I guess it wasn't really far because it's 36 minus 20. So it is 16 omega naught to the fourth over 2. So I was very close. Where's that at? I did the simplification and made it 16. But see, this number here was off that threw the whole thing off. There's negative 7. So, I mean, the simplification brought it closer to what it should be, but the lead number was so off that it messed it all up. So this equals negative 6 omega naught squared uh, plus minus 4 omega naught squared divided by 2. So this equals what? Negative 2. I'll just do it separately. So so let's say x1 equals negative 6 omega naught squared plus 4 omega naught squared divided by 2. So that's negative 2 omega naught squared divided by 2. So that's negative omega naught squared. And that's omega 1 squared. So x2 squared, well, x2 equals negative 6 omega naught squared minus 4 omega naught squared over 2, which equals negative 10 omega naught squared over 2, which is omega 2 squared equals negative 5 omega naught squared. And that is what Professor said the answer should be. So I'm almost to the part where I need to get the last thing I need to get. Did I miss a negative somewhere? I had a negative. Yeah, I think that seems right. Let me know if y'all see a negative off or something. And Amaya says the name of the formula is the quadratic equation. Yes, quadratic equation. It's funny how we forget the names of formulas we use every day. Happens to me a lot. Yes. Because I need to pay attention to names more. Probably, I think generally I don't pay attention to names, like even names of people. Like I know people and interact with them, but I just don't often focus on the names. I need to start doing that more. I had a professor, matter of fact, the professor for this waves class I took the first time, he remembered everybody's names. Seems like within a few weeks he remembered the whole class's names. But he seemed to pay a lot of attention to that. So I noticed he put a lot of time towards remembering names. All right. Boom. So we're looking good. So now what I have to do is get the normal modes. So this is the normal, what's it? Oops. Normal mode frequencies. And now I need to get the normal mode vectors functions. What would it be called technically here? Normal equations. I'll just call them vectors. All right. So we were here. I'll just call this the characteristic equation. Pretty sure that's not the right name for it, but I'll just call it that. So I'll go back to the characteristic equation. Oh, hold up. I didn't mean that one actually. I meant, yeah, it is that one. We're going to put the lambda i's in. I'm going back to my characteristic equation, and I have to plug omega I and solve for, which is A. All right. So this is the part I missed. So we have x of t equals a cosine omega t minus phi. So x dot t equals, well, we could just actually stop there. So if I plug this in, let me make sure I didn't drop anything off. Yeah, it looks good. Or just the x. Yeah. So we've also plugged this in. I'm going to copy some stuff down to save some time rewriting stuff. Mm, This x2 equals 0. I'm doing this right. So I'm going to go ahead and pull up the textbook, even though they do it a different way. And Ahmad says, for example, in vector calculus, you forget the name or fail to recognize that a certain differential equation is a Poisson equation. It is almost impossible to know how to solve it. Thinking back to my electrodynamics class, I can see the relevance of that with the Poissons and what do you call it, Laplaces. But I think even then, I still kind of remember the look of it. Like Poissons was something like this. You have the zero at the end. So this is Laplace. And Poisson was like this, which you had the density over here, something like that. It was something like that. Whatever Laplace was zero, and Poisson was with the density on the other side. But it's interesting how these people get these names. Field is not square, something like that. I remember there was Laplace and Poisson, which I'm going to have to do in a little bit. In this same class, actually, that we're looking at right now, the foundations class, we pretty much reviewing all of undergraduate physics in a semester. Of course, to cut out some things. Awesome. All right, so I think this is where we at. Let me just check. I'm going to make sure that I got my omegas, the normal frequencies. I know these are right. Uh, these complex, right? I'm trying to get the amplitude. So let's look at this. Solve the equation for the vector A. I hate the way the book does it. Probably just because I'm not used to that way. All right, let's do this thing. So I have -3 omega naught squared minus omega squared x1 plus 2 omega naught squared x2 equals 0. And I have 2 omega naught squared x1 minus, I'll just keep the negatives intact since I did it for the first line, 3 omega naught squared minus omega squared. I'm going to check something really fast. We have this equals 0. I got my x2. So we have this, and I should be able to solve for x in this way. 2 equations, 2 unknowns. This is the way to do it. Let's see. Okay. So one detail we have to do is I have x1 c. It's going to be a1 cosine. Is this omega 1 t minus phi 1, and then x2 t equals a2 cosine omega 2 t minus phi 2. No, we have to just plug in what's going to be the default frequency. This is going to be the default minus phi, and x2t is going to be a2 cosine omega naught t minus phi. And this may be different, but I'm not sure. Thank you, Ahmad. I appreciate it. So we'll have, and the thing about this is everything is going to be multiplied by the same stuff. Uh, is cosine, is phi the same? I don't remember if phi is the same. Let me check on that. Yeah, phi is the same for both. And alpha is the same for both. What I'm trying to do now is sort of mesh my way of doing it with the book way of doing it, which they don't divide by m. Oh, and you do have different phi's. All right. So we know it is phi 1 and phi 2. What the book is doing is, like, I like the cosine way because that's the way I did it. But they're saying A is A1, A2, and they're calling that alpha 1 E negative I delta 1 and alpha 2 E negative I delta 2. And that's that. So this is basically the exponential form of what I have. This is basically that. and basically that. Well, I mean, I should have a sign up in there as well. When you convert it, there's a sign with the imaginary. We won't worry about that right now. And they're finding a 2, a 2. All right, so they are finding the so I think I'm not too far off here. So let me just go ahead and make this whole thing one color. So I have -3 omega squared at 1 minus omega squared x2 plus 2 omega naught squared x2 equals 0, and 2 omega naught squared x2 minus 3 omega naught squared x2 minus omega squared x2 equals 0. Should be a 1 in the front. It should be 1. So I distributed the x1 to the 3. I distributed the x1 to that by itself. And now it's still by itself. And I distributed the x2 to the -3 and the x2 to that one by itself. All right, so now we're in a position where we can put in our omegas. So we put in omega 1. This is actually omega I. So omega 1 equals, what was my omega 1? Negative omega naught squared. These are the equations I'm solving. So we have -3 omega naught squared x1 minus plus omega naught squared x1 plus 2 omega naught squared x2 equals 0. Then we have 2 omega naught squared x1 minus 3 omega naught squared x2 minus plus omega naught squared x2 equals 0. So now we have -2 omega naught squared x1 plus 2 omega naught squared x2 equals omega naught squared x1 plus omega naught squared x2 is negative equals 0. And for the second line, we have 2 omega naught squared x1 minus 2 omega naught squared x2, which equals 2 omega naught squared x1 minus, equals omega naught squared x1 minus omega naught squared x2 equals 0. So if I solve both of these, they're both going to be omega naught squared x1 equals omega naught squared x2. So x1 equals x2. X1 equals x2. So we have so I'll put this in the right column. They're moving together. So x1 equals x2. So that means that x vector equals x1 t x2 p, which equals so this is going to be 1 x1 equals 1 x2. The normal mode is 1 1 equals a cosine omega 1 p minus. So in this case, a normal mode is moving in the same direction and same amplitude. If I'm understanding that correctly. All right. Let's do the next one. And it should be everything that we have here, just with the different value for the frequency. All this 1, 2, everything is the same. Plugging that in. I have to copy the whole thing. I can just copy the second page. I'm gonna have to put this 1 here. And I can call this 2. Right. So And I'll highlight in red the things that I change. So omega 2 squared equals, what was it? -5 omega naught squared. 5 omega naught squared. Changing this here. So this is going to be 5. This is going to be 5. So then we have positive 2. It's positive. And this is going to be also positive 2. So we're going to make this positive. So now we have negative WO squared x1 equals WO squared x2. Now we have negative x equals negative. So negative, when you have a negative on 1. So it's x omega 2, x omega 1, omega 2, omega 1 equals negative 2. And now they're going to be going in opposite directions. So same amplitude, but one is going the wrong way, the other one is going the other way. And you're going the opposite direction from the normal mode. We could just repeat like that forever, continuously. And this is going to be omega 2, moving in the opposite direction. Right, so I think that's it. So I'll go ahead and take a break. That was, I think, everything we need to do for a coupled oscillator. I'll send it to my professor, see what he says. And I'll be back later to do some calculus of multiple variables. So some of you were asked earlier, be a good break. And we'll see how that goes. I'll do like a simple multivariable problem. Be a good break from all of this graduate stuff and review stuff. Let me actually come back and finish reading my what I started earlier. I was doing some graduate reading earlier, so I'm pretty sure I'll finish that later. So you can look for me later and I'll finish that graduate level reading. So take a break, get something to eat, come back, do some linear algebra. Maybe I'll read before I do linear algebra, but definitely I'll come back and do some more graduate reading. Thank you everybody who watched and popped in. Thanks for everybody who posted a comment, asked a question, pointed out a correction. And hopefully you liked and subscribed if you haven't. I'll see you all next time.